for discussion. Let's see if I'm successful. So when you teach a formal languages course, right, you talk about all kinds of state machines, and eventually that leads to Turing machines. But in this process, typically in a pencil and paper course, students get frustrated because they get marked down for buggy machines, they get marked down for proofs based on buggy machines, and this goes against their computer science education because they're trained to what? To implement, to run programs, to write unit tests. In other words, to get immediate feedback on their designs. Right? So what can we do? So this is a programming languages course, and we're in what? The domain-specific language era. And so what we want to do is provide them with a DSL, which Tiana introduced as FSM. And so FSM does all kinds of things, right? So you can program NDFAs, DFAs, Turing machines, PDAs, multi-tape Turing machines, regular grammars, context-free grammars, context-sensitive grammars, regular expressions. The whole gamma is part of FSM. So I'm going to talk only about a small piece of that, which is the composition of Turing machines. So to build a Turing machine, we have a constructor, and every Turing machine has 5 things. So there is a set of states, an input alphabet, a set of transitioning rules, a starting state, a set of final states, and if the machine is designed to decide a language or semi-decide a language, the accepting state, which is optional because not all Turing machines decide a language. So here's a simple example of a Turing machine that moves the head to the right 1 space. So what we do is we specify the machine. So here we're saying that before the machine executes, we have the left-hand marker and the word on the tape, and the head position I is some position greater than 0. And in the post condition, the tape is not mutated, but the head has moved 1 position to the right, so it's k plus 1. So if we have 2 states here, S and F, and the input alphabet is A, B, the starting state is S, and the final state is F. And you see that no matter what state you're in, if you read an A, a B, or a blank, you simply move to the right and go into the final state F. And that will move the machine 1 to the right. And then students, right, can write unit tests. So for example, we can show the transitions on our right machine on this input, and then they could see that it goes through those 2 transitions there. Right? Turing machines can also mutate the tape. So here's an example of a mutator in terms of a Turing machine. So precondition, we have our word on the tape, the position on some position k greater than 0, and that position contains S on it. And in the post condition, the tape is mutated to the word is mutated to W prime. The head is unmoved, but now the value at position I is to a blank. And if we look at the transition rules, right, we have that no matter what state, no matter what is read, we simply write the blank to the tape and move to the halting or to the final state. And then again, students can write tests to make sure that, to validate, right, that their design works. By the way, feel free to interrupt me if you have any questions. Okay, so of course these easy Turing machines are not all that interesting. What we really want to do is build more complex Turing machines because in theory Turing machines can do everything, right? So how do we do that? Right, so here's a slightly more complicated problem. Move the head 2 spaces to the right. So if we did this using just our Turing machine constructor, basically what we would have is 3 states, our starting state, an intermediate state, and a final state. And then from the starting state, no matter what is read, we move to the right, and we transition to the intermediate state. And then from that intermediate state, no matter what is read, we move to the right and move into the final state. Right? And basically what has happened here is that we repeated the code to move to the right twice. Now, if we're only moving to the right twice, that's fine. But if we want to move to the right 10 times, 20 times, or 50 times, that's not the type of coding that we want to do, right? So we need an abstraction, And so to avoid that type of repetition, we use Turing machine composition. Okay, so here's what we really would like to write. Right? We want to have our tape, our initial tape, in the head at some position k, and then when we execute the machine, the tape is unmuted, but the head is moved 2 positions to the right. And what I would like to do is to take my right machine and use it twice. So here's how I would write it. Execute R, then execute R again, and halt. Now to write that type of things, of course, we need a syntax. So here's the syntax to write composed Turing machines. It could be empty, which means just halt, don't do anything and halt. Or it can be the sequencing of a machine and then the rest of the machine. Or it can contain a label, and the label indicates where a certain machine starts, and this is what's used for looping. And then there could be unconditional jumps, which simply keyword go to and the label that you're jumping to. And there could be conditional branching, which provides the options of the symbol that's read and then the label that you want to jump to. In addition, we can abstract away the element that's being read by declaring a variable, and then the scope of that variable is the machine that's enclosed inside the parentheses here. And then if we have a variable declaration, then of course we can use that variable to mutate the tape and then continue. Okay, so basically there's 7 different types of expressions. And let me illustrate how you would design these. Right, so we saw how to move twice to the right. We just write R twice and we're done, right? How about something a little bit more complex? Move to the first blank to the right. Now what we want to do there is, right, we want to move to the right, and then we have to check what's being read. If it's not a blank, loop back and move to the right again and repeat the process. Okay, so here we have an arrow, and this is why we need labels, because these arrows indicate this is a point where you have to jump to. So here's how we would implement this. That arrow is label 0, and at label 0 we have the machine that moves right, and then we have a branch. And if it's A or B, we branch back to 0, and if it's a blank, we go to 10, and 10 is the machine after that is empty, so the machine will halt. Okay, so and then you can see in the tests that this machine works as it's supposed to. So if, let's look at the one test here, right, we're in position 2 here, so that's the first A, and then we move to the first blank to the right, and that would take us to this blank here, which is in position 6. Okay. Okay. Now, how about this example where we're writing the 2 elements to the right to be the same as the element that's currently being read? So in this case, we want to declare a variable s that abstracts over what's being read. We move to the right, we write that variable, that value, we move to the right and write that variable again, and the implementation looks exactly like the picture. Right? Here we declare our variable, so whatever is being read, that's the value of s. We move right, and then we can use s to mutate the tape. And then if you could look at the examples, right? So here, for example, we're in position 1, that's over the A, and we want to write 2 A's after that. So what happens is we write that A, and we end up in, the head ends up in position 3 of the tape. Okay, so this brings us to a more complex example. This is not the example in the paper, so hopefully with what's in the paper and this, you have 2 examples that you can kind of work with and play around with. But what we want to do is add 2 natural numbers. Any idea how? How do we add 2 natural numbers? Yeah, you look like my students in class. I have no idea how to add 2 natural numbers, right? So it's at this point where I have to remind my students to remember everything that they've been taught and everything that they've been learned, right? So for somebody who's followed a design-based program, the natural thing to do is to think about the structure of the data that you want to process. And this means defining it. So a natural number, in our case, will be either a list containing only a blank in it that represents 0, or it can be a list that contains a D and then followed by a natural number. And here are some examples, right? So that represents 0, that represents 3, and this represents, if I can count right, that represents 8. Correct? Everybody got that? So pretty straightforward. Okay, so now we specify our machine. So we start with the blank before the A, the head on the blank before the A, then we have A, then we have a blank before B. That's where we start, and what we want at the end is to have the starting blank, the sum, and then the head on the blank after the sum. Okay. Okay. So how do we do that? Whoops, yeah. So what we want to do is reason about that structure. And this is, right, animated problem solving or how to design programs, bread and butter. So what we're going to do is we're going to move the head to the right. Remember, it's on the blank before the A. And then there's two options there. Either A is 0 or it's not 0. So if A is 0, we'll branch this way. If A is not 0, we'll branch this other way. Now, if A is 0, what do we want to do? Well, we want to figure out if B is 0. Right? So now we say, okay, move to the right twice, and now check what B is. So if B is not 0, then we have to figure out a machine to process A equal to 0 and B not equal to 0. And if B is 0, then we look at this situation where A is 0 and B is 0. And then what do we do when A is not 0? Well, we have to skip all of A to get to B to figure out if it's 0 or not. So we go to the first blank to the right, we move to the right, and then the same thing. We determine if B is 0, or we determine that B is not 0. And what we've done there, right, is this is your bread and butter divide and conquer, right? We've divided into, hopefully, 4 smaller problems. But usually when you use this type of structural recursion, the subproblems are always easier. So we're in safe ground here. Okay, so let's look at the 4 cases independently now. So if both of them are not 0, what do we do? Well, we're going to start with the D, with the first element of A, which is that first D. We're going to move to the blank that's between them. We're going to mutate that D, the blank, to a D. So now we have A plus B plus 1 on the tape. Then we're going to move to the blank at the end, after B, move to the left, and then mutate that last D into a blank. And now you have, you see, the post condition. We have A plus B between the 2 blanks at the beginning. Okay, and then we're going to do something similar for the next case. A is 0 and B is not 0. And it turns out that for that case, the same steps apply. So by this type of analysis, we discover that these 2 cases, when A is 0, we apply the same rules. So we can implement that like this. Move to the first blank to the right, write a D, move to the first blank to the right, move left, blank out whatever is there, and then halt. Okay, so we have part of our solution already. Right, this branch here that used to break into 2 branches is now solved using that code. Now we're going to do the 2 other branches. So what if both of them are 0? Well, if both of them are 0, right, remember we've already moved to the first blank to the right and to the right, so we start there in that configuration. And since the sum is 0, all we have to do is move the head to the left and halt. And if it's the last case where, yeah, that's how we implement. If it's the last case, let's go to the last case, here we go, where B is not 0, then we're on the first D of the B, we move to the right. And now you see we have the answer on the tape, right? A, 0 plus B is just B, but it's in the wrong position. So we shift it to the left once, and that puts our head at the end. We move to the first blank to the left, shift again, and now we have the post condition, right? The sum is there. So that part is implemented this way. Left, first blank to the left, shift left, halt. Right? And now we have all the pieces that we need to actually code up our machine. Right? So this is what it looks like, right? So there's 4 arrows, so you need 4 labels, plus the label where the machine halts. Right? So 100 is the label when A is 0, 200 is when the A is not 0, 300 is the machine the part of the machine that's going to process when A is 0 and B is not 0, and 500 is when A is 0 and B is 0. And then 1,000 is just when you want it to halt. Okay? Now, how do we know that this is correct? By the way, just so that everybody's a believer. Where is it? Okay. Let me run this. So here's an example, right? So in this case, they're both not 0, and when I run that, you see that the tape ends up with the sum of A and B on it. Okay? Okay. So now, how do we know that this is correct? Right? Well, key word in this course is formal, right? Formal reasoning. So we want to use formal methods. So we're going to teach, we have students do correctness. And for that, we just use Hoare logic. Right? So we start with the configuration of the tape. And at the beginning, the head is on the blank before the A. Okay, so once that's done, what's the first thing that it does? It moves to the right. So what's the configuration after that? Well, if it moves to the right, there's two options, right? We already know this from our design. Either A is 0 or it's not 0. If A is 0, the head is over a blank. If it's not 0, the head is over the first D of A. Okay, so then what? Now we branch, right? And that's going to tell us which of these two situations we're facing. And so if we branch to 100, then we know that where A is 0, we're reading a blank. And if it's not a blank, then we're reading the first D of A. And we're in this configuration. And now we keep adding the Hoare triples and just drag these assertions through the machines that are part of the program. So we move to the right. So the right, that's easy. One to the right. We move to the right again. So it's either here, reading a blank because B is 0, or it's on the first D of B. And then we branch. And that would be to the 500 or to the 300 for both of those cases. Now, more interesting, what happens when A is not 0? We move to the first blank to the left. So we're on the first D of A. First blank to the right, is there, right? So now we're after A. The head is after A. And we write the D there. Right, so that's easy. So now that blank is mutated to a D. And then we move to the first blank to the right. And again, right, that's the first element of B. It could either be 0, it could be blank if it's 0, or it can be a D. And then again, we move to the left. And what we want to do is whatever's on the left, we're going to turn it into I'm sorry, where I got lost now. Move left, yeah. And then we turn that into a blank. And once you turn that into a blank, if you look at that, right, that's our post condition, right? We have the sum in the right place. So we can safely branch to halt, which is label 1000. And we're going to do the same thing for the branches as 300. I won't bore you with the details, right? Everybody gets the gist. And the same thing, right? But the important point to point out to students is that no matter which path is executed in the Turing machine, the post condition is always met before jumping to the halting label. Okay? Okay. So, Tiana kind of jumped the gun on me, so if you like this approach and you would like to adopt it, there it is, right? It's coming out. It'll be in December. It'll be in print. So I encourage you to take a look at it, adopt it. Send me lots of questions, because the biggest complaint I always got was, I want to do this, but we need a textbook. So I heard your complaints. There's the textbook. FSM is available for free on GitHub. So just search my last name in GitHub and you'll see FSM. Okay. And for the discussion, if you guys want to try your hand at designing a little, right? There are a few problems you can try out, or if not, or if you have questions, feel free, but I'll let you guys discuss now.
All right, usual time for group discussion.
proof. At SPLASH-E, we practice on the breach, so we have small group discussions, and then we open up It is stolen directly from my server with great statements.
Not to worry, I'll also visualize this.
It's also very used at SPLASH-E. The button is stolen from my server as well. Oh, awesome. So what are your thoughts?
I've always attempted to introduce some kind of methodology, but I've always done it in a
Blow it away.
I do use
How much time do you think it will take us to design this?
I have to look at that, so
Not 4 minutes.
I would worry that we don't spend enough to get you started.
I got that, that whole thing, your guys want I saw some shots there. If they knew something on it,
I can think of myself.
have to see, sir. You got a person not feeling too well. You got a guy not feeling too well.
And I think that makes sense, like, parentheses comes in. Well, like, here's problem strongly, right, and we like ignore everything. Here is there was problems research on the term, why is it not
How do you
like
approach
what instructions that learning curve would be, because
You try to use the tools to
like
approach
programs.
the
Well, assume you're undergrad.
structural
Like,
recurrence.
and I'm able to write, I make them do it, if I would like write 20-line programs in like.
Incredibly simple.
As like, hey, look at my real world applicability of my theory. You're gonna learn a new language to help us.
In the context of formal languages course, you can change
So it's the whole formal languages course is programmed.
Yeah.
So all the machines, all the grammars, everything is
That's very different than most formal languages.
That's what I was saying at the beginning, that it's pencil and paper, which is more difficult.
Right.
Now they do everything inside a programming language, everything. And there is no pencil and paper.
For context, which
This is juniors and seniors, so upper level students.
okay, so they already have like at least a couple of years.
They're not beginners. Yeah, they're people who are graduating that year or graduating the next year.
Okay,
Towards the end.
so they already know how to program. Oh, okay.
But intro, it's classic. And then I actually teach HTML levels. So.
All right, I guess we can bring the discussions to the speaker. Questions, if you raise your hand, the mic will magically get to you.
I had a brief technical question. So there were the pre and post comments. Are those parsed and like used as part of FSM? Or are there just comments? Cool.
Picking up off of that comments question, do you think it would be feasible or viable to actually use those comments for something? So that all that reasoning that you did, do you think there could be a way to like parse those comments and then automatically reason about the machine? Or maybe I'm being too ambitious here.
No, I don't think you're being too ambitious. It's just I don't want to parse the comments. What I want to do is I want to re-implement this using Calc or something like this, and then
Okay.
have an automatic theorem prover.
All right.
Prove,
yeah,
prove
that's that kind of stuff,
Prove
yeah.
that the machines work correctly.
Oh,
So
that's
that's the ultimate goal. This is just
That is
work
super
in
interesting.
progress. Right?
Thank you.
We have to write these down, proofs.
Yeah.
No, fine.
Yeah, but if you could have like an automatic proof, like this machine works, here's the proof,
Yeah,
it's
every
automatic,
time-
that'd be super cool.
Yeah.
It's already
Every time
super
we
interesting,
do it,
I'm not
we
like
have to write
criticizing.
the proof.
Don't be shy.
So this may just be the fact that I'm a compiler developer, but when I was looking at this, I was like, wow, it would be actually kind of fun to write the thing that takes I assume that you provide the sort of compiler from your little DSL to the actual thing.
Yes.
But I also think that there is a certain category of nerd, and I may be sort of one of the only people in that who are like, oh, well, but what if I could do that part myself? Like that's an interesting advanced exercise, maybe.
Yeah. So one of the biggest motivations was the motivated development of FSM was that students were not getting non-determinism. They just completely didn't get it. So I decided that what we need is a programming language where this is a feature and not have them worry about how to implement non-determinism. So it's a compromise.
Other questions?
Okay.
Okay, I guess we can thank the speaker then.